The largest black hole we have ever found spent almost its entire existence doing nothing at all. For hundreds of millions of years it simply sat in the dark, at the centre of a swarm of galaxies 5.7 billion light-years away, holding a mass that may reach 100 billion times that of our Sun. Our own galaxy's central black hole, the giant that anchors 200 billion stars, is a mere 4 million solar masses. This thing could be 25,000 times larger. But here is what the textbooks leave out. It is too big to have formed in the time the universe has existed. Its edge is so wide that light itself needs 3 weeks to cross it. And after all those ages of silence, in the light now reaching us, it has begun to feed again. The more closely we look at it, the less it behaves like a black hole at all. Get comfortable. Hit subscribe if you're new here. Because by the end of this, the words black hole are going to feel far too small for what is actually out there. Now let's slowly ease into this. Part 1. The thing that is awake. There is an object at the far end of a line you could draw from where you're sitting, 5.7 billion light-years long, and for almost all of the time that line has existed, that object did nothing at all. It sat in the dark. It held its position at the centre of a swarm of galaxies. It waited. And then, sometime in what we would call the recent past, after what may have been hundreds of millions of years of near total silence, it began to move again. It began to feed. We call it Phoenix A, and it is, by our best reckoning, the largest single black hole anyone has ever found. That sentence is easy to say, and almost impossible to hold in the mind, so let me try to give it some weight before we go any further. The galaxy you live in, the Milky Way, contains something like 200 billion stars. It carries clouds of gas and dust like years across. It is wrapped in a halo of dark matter we cannot see but can feel through its gravity. And at the very centre of all of that, holding the whole slow carousel together, is a black hole of about 4 million times the mass of our Sun. That black hole has a name, Sagittarius A star, and by the standards of our neighbourhood it is enormous. Phoenix A, at the upper end of what the measurements allow, may be around 100 billion times the mass of the Sun. Set that beside the 4 million at the centre of our own galaxy, and the comparison stops being a comparison. Phoenix A could be roughly 25,000 times more massive than the object that anchors everything you have ever known. It is not a larger version of the same thing. It is a different kind of thing, in a different weight class, obeying rules that our textbooks were not entirely written to describe. And that is the first strange note in this story, the one we will keep returning to. The closer we look at Phoenix A, the less the word we use for it seems to fit. The word, of course, is black hole. You have a picture in your head when you hear it. Most people do. A small, dark, hungry point in space, a drain that light itself falls into, a thing that would tear you apart if you drifted too close. That picture is not wrong exactly. For most black holes it is a fair enough sketch, but hold on to it lightly, because over the next couple of hours it is going to come apart in your hands, and the thing left standing in its place will be stranger and quieter, and, in a way I will try to earn, more unsettling than the picture you started with. Consider where Phoenix A lives. It sits at the centre of what we call the Phoenix Cluster, a gathering of galaxies bound together by their own gravity, out in the direction of the southern constellation the cluster is named for. This is not a modest structure. When we add up everything in it, all the galaxies and all the gas and all the invisible matter, we arrive at a total of around 2 quadrillion times the mass of the Sun. That is one of the most massive single structures we have ever identified anywhere in the observable universe. And within that structure, inside one central galaxy that dwarfs everything around it, sits the black hole we are here to talk about. Now consider what it is doing. This is the part that turns Phoenix A from a record on a list into a genuine puzzle. Most of the truly enormous black holes we know about are quiet. They grew to their staggering sizes long ago, ran out of easy food, and settled into something close to sleep. The biggest ones tend to be the sleeping ones. That is the pattern. That is what we expect. Phoenix A breaks the pattern. Right now, in the present tense of the light reaching our telescopes, it is not sleeping. It is feeding, and not gently. Gas is pouring down onto it. Around it, the central galaxy is lighting up with newborn stars at a rate that has almost no equal anywhere we have looked. Something woke this thing up, and it has been eating ever since. So this is a story about a monster we did not know existed, in a place we could not see, doing something we cannot quite explain. Each of those three pieces matters. We did not know objects this large were possible until the observations forced the issue. We could not see the cluster it lives in with ordinary eyes, and I will tell you the genuinely odd way we finally noticed it. And we cannot fully explain how it got so big, or why, alone among the giants of its kind, it is awake. Every one of those gaps is a place where our confidence quietly runs out. Let me set the stakes of the whole video plainly, so you know what we are actually chasing across the next couple of hours. There are really three questions at the centre of Phoenix A, and each one is a place where our confidence quietly gives out. The first is how large it truly is, because the mass estimates run frighteningly high and refuse to settle into a single agreed number, and the largest of them push against the very edge of what we think is possible. The second is how it came to be, because when you take our best account of how such objects grow and try to build one this heavy, you find there has not been enough time since the beginning of the universe to do it, which means either the object formed in some way we do not understand, or it was born already enormous. And the third is why it is awake at all, because giants of its kind are supposed to be sleeping, their fuel long spent, and yet this one is feeding hard, in a place where a balance that holds across the rest of the universe has somehow broken. None of those three questions has a clean answer. That is the honest state of things, and it is exactly why this object rewards a slow, patient look. We are not going to arrive at a tidy resolution where everything clicks into place and the mystery dissolves. We are going to do something more interesting, and in a way more truthful. We are going to walk right up to the edges of what we know, feel where the ground gives way, and stand there for a while in the company of a thing that our own science says should not quite be possible. The point is not to solve Phoenix A. The point is to understand it well enough to feel the precise shape of what we cannot yet explain, because that shape, that outline of our own ignorance, is one of the most fascinating things the universe has to show us. I want to be careful here, because this is a channel that tries to earn its wonder rather than manufacture it. Phoenix A is not a danger to you. It is 5.7 billion light-years away, which is a distance we are going to have to work hard just to feel the edges of, and it exerts no meaningful pull on anything in your life. Nothing about it threatens the Earth. The unease this story produces is not the unease of danger. It is something slower and harder to shake. It is the feeling of learning that the map you were handed, the one with the neat categories and the sensible upper limits, has a region on it that simply does not obey the key in the corner. It is the feeling of an object so large that it forces you to ask whether the word you have been using for it means anything at all. And there is one more thing, before we begin properly, that I want you to carry with you. The light we are collecting from Phoenix A right now left it before the Earth existed. It began its journey across 5.7 billion light-years of space at a time when there was no sun yet in our part of the galaxy, no rocky world cooling into oceans, no life, no us. In all the time it took that light to cross the gap, our entire planet formed, cooled, grew an atmosphere filled with living things, and eventually produced creatures curious enough to build the instruments that would catch it. And through every second of that immense stretch, Phoenix A simply continued being what it is. Still there, still enormous, still, in the light we're only now receiving, awake and feeding and hungry. I want to say a little more about that word dormant, because it does a lot of quiet work in this story and it is easy to pass over. When we say a black hole is dormant, we do not mean it has gone anywhere or become anything less than it was. All of its mass is still there. All of its gravity is still there. The territory it commands is exactly as large as ever. What has changed is only that it has stopped eating, and a black hole that has stopped eating gives off almost no sign of itself. It does not blaze. It does not drive great beams of energy out into its galaxy. It simply holds its position and its pull, silent and dark, a giant with nothing falling into it. For most of the history of Phoenix A, this is what it seems to have been. Present, immense, and quiet, giving the universe around it no reason to notice. And then something changed. Gas began to fall toward it again, and when gas falls toward a black hole, it does not simply vanish quietly over the edge. It piles up, it circles, it heats through friction as it crowds and grinds against itself, and it begins to glow, fiercely, before it finally crosses the boundary and disappears. A feeding black hole is one of the brightest things in the universe, not because the black hole itself shines, but because the matter falling into it blazes in its final approach. So when I tell you Phoenix A is awake and hungry, I am not being poetic. I mean that after ages of silence, matter is once again pouring down onto it, lighting up as it falls, marking the position of a giant that spent most of its existence giving off nothing at all. The awakening is not a metaphor. It is a change we can actually see in the light. Let me show you how we found it, and then let me show you how big it really is, because until you feel the size, none of the rest of it will land the way it should. Part 2. The universe we were comfortable with. For a long time, the universe of black holes was a comfortable place, at least on paper. It had two kinds of residents, and between them a sensible amount of empty space, and that was more or less the whole story. If you had opened a textbook 25 years ago and looked for the chapter on black holes, this is the picture you would have found, and it is worth spending a little time inside it, because you cannot feel how strange Phoenix A is until you have first stood in the tidy world it broke. The first kind of black hole was the small kind, though small is a word we will have to use carefully for the rest of this video. These are the corpses of dead stars. When a star much larger than the Sun runs out of fuel, it can no longer hold itself up against its own weight, and its core collapses in on itself in a fraction of a second, and what is left behind is a black hole. These stellar mass black holes, as we call them, range from a few times the mass of the Sun up to perhaps 100 times. That is the entire range. A star lives, a star dies, and it leaves behind an object in that band. We understand this process well. We can watch it happen. We can even hear it, in a sense, when two of these black holes spiral together and merge and send a tremor through the fabric of space that our detectors on Earth can feel. This category made sense. It had a clear origin, a clear range, and clear physics. The second kind was the large kind, the supermassive black holes that sit at the centres of galaxies. Our own Sagittarius A star belongs to this family, at 4 million solar masses. Others run larger, into the hundreds of millions, and some reach a few billion times the mass of the Sun. These are the anchors of galaxies, the still points around which hundreds of billions of stars turn. We were less certain about exactly how they came to be, but we had a working story, and the story involved a lot of time and a lot of patient eating, and we will get to it, because Phoenix A is going to break that story in a very specific way. Between these two families, the small and the large, there was a gap. A black hole of a few hundred times the Sun's mass, or a few thousand, or even a few tens of thousands, was a rare and uncertain thing, hard to find and harder to confirm. And beyond the large family above a few billion solar masses there was, as far as the old picture was concerned, nothing. That was the ceiling. That was the top of the world. You had the dead stars at the bottom, the galactic anchors near the top, a thinly populated middle, and then an edge beyond which the universe was assumed not to build. It was a clean picture. It fit on a single page. And like a lot of clean pictures, it was clean partly because we had not yet looked hard enough to find the mess. I want to pause on why a picture like this feels so reassuring, because the feeling matters as much as the facts. When you can sort the universe into a few labelled boxes with sensible limits, you get to believe, quietly, that you understand it. You get to believe there is a largest possible thing, and that we have found roughly where it sits. The mind likes ceilings. It likes knowing that beyond a certain point the numbers stop. A black hole of 1 billion suns is already almost beyond comprehension, and to be told that this is close to as large as they come is, in a strange way, a comfort. It means the universe, however immense, is bounded in this respect. It has an upper shelf, and we can see it. Now, the physics behind that ceiling was not arbitrary. There were real reasons to think black holes could not grow without limit. A black hole grows by pulling in matter, but the matter does not fall in quietly. As gas spirals toward a black hole, it heats up, and hot gas glows, and that glow pushes outward. The brighter the region around the black hole becomes, the harder the outward pressure of light pushes back against the very gas that is trying to fall in. Past a certain brightness, the pushing out balances the falling in, and the black hole effectively chokes off its own supply. It cannot eat any faster no matter how much food is available. This self-imposed speed limit is a real feature of the physics, and it means that even a black hole surrounded by an ocean of gas can only grow so quickly. Multiply that speed limit by the age of the universe, and you get a rough sense of how big a black hole could plausibly become, and the answer, for a long time, seemed to sit comfortably below the ceiling we had drawn. The mention of hearing two black holes merge is not a figure of speech, and it is worth a moment because it shows how much our confidence about the smaller family rests on solid ground. When two stellar mass black holes spiral together and finally merge, they shake the fabric of space itself, sending out ripples that spread outward at the speed of light, faint distortions in distance that stretch and squeeze everything they pass through by an amount almost too small to imagine. We have built instruments on Earth sensitive enough to feel those ripples as they wash over us, detectors that can measure a change in length far smaller than the width of a single atomic particle. And when the signal arrives, we can read from it the masses of the two black holes that merged, confirming that they sit squarely in the range we expected for the corpses of dead stars. So the lower family is not a guess. It is something we have weighed by watching stars die and by feeling the tremor when their remnants collide. That is part of why the upper end of the scale was so unsettling when it broke open. The bottom of the picture was on firm footing, which made the failure at the top feel less like a small correction and more like a genuine hole in the map. So there we were, standing in a universe that made sense. Dead stars leaving behind modest black holes, galaxies anchored by larger ones, a ceiling overhead held in place by good physics, above which we did not expect to find anything. If you had asked an astronomer at the turn of the century what the most massive black holes in the universe weighed, they would have given you a number in the billions of solar masses and felt reasonably safe doing it. It is worth pausing on how we even know the masses of these objects, because at first it sounds impossible. You cannot put a black hole on a scale. You cannot travel to one and weigh it. Everything we know about how heavy a black hole is, we infer from its effect on the things around it. The most common method is to watch how fast stars and gas move near the centre of a galaxy. Gravity sets the speed. The more massive the central object, the faster nearby stars must travel to hold their orbits without falling in. So astronomers measure those speeds carefully across the crowded centre of a galaxy and work backward to the mass that must be sitting there to produce them. It is a form of weighing at a distance, reading the mass of an unseeable object from the motion of the visible ones caught in its pull. That method is powerful, but it is also where a great deal of the uncertainty enters, and it is worth keeping that in mind as the numbers climb. Measuring the speeds of stars at the centre of a galaxy, hundreds of millions or billions of light years away, is delicate work, and different techniques, different assumptions about the shape of the orbits and the amount of unseen matter can give answers that differ by a lot. This will matter enormously when we come back to Phoenix A, because the very largest mass estimates for it carry the very largest uncertainties. But the basic principle is sound, and it is how the first cracks in the tidy two-family picture appeared. Astronomers weighed the centres of galaxies by watching the stars swing around them, and every so often the answer that came back was not just large, but impossibly large, far above anything the comfortable old ceiling was supposed to allow. And then the observations started coming in that did not fit, not a little outside the lines, orders of magnitude outside them, black holes at the centres of galaxies that were not a bit too heavy, but grotesquely, impossibly too heavy, sitting where the old picture said nothing should be. The ceiling, it turned out, was not a ceiling at all. It was just the highest point we had happened to look, and once we started finding what was above it, the comfortable two-family universe of black holes quietly stopped being true. Let me show you the first cracks, because they came before Phoenix, and they are the reason we had a word ready when Phoenix finally arrived. Part 3. The cracks in the ceiling. The first cracks appeared in the early 2000s, and they appeared in a way that is easy to underestimate because at first each one looked like a single odd measurement rather than the beginning of a new category. Astronomers would point their instruments at the centre of some galaxy, measure how fast the stars near the core were moving, and use that motion to weigh the black hole holding them in their orbits. Most of the time the answer came back sensible, somewhere in the expected range. But every so often the answer came back wrong, not slightly wrong. Wrong by so much that the first instinct was to assume a mistake had been made somewhere in the calculation. Take a galaxy called NGC 1277. It is not a remarkable galaxy to look at. It is fairly compact, not especially large, the kind of object you would pass over without a second glance in a survey of thousands. And yet when astronomers weighed the black hole at its centre, the number that came back was, by the original estimates, as high as 17 billion times the mass of the Sun. 17 billion. In a galaxy that modest. To put that in perspective, That single black hole was estimated to hold a substantial fraction of the entire mass of its host galaxy, which is not supposed to happen. Black holes, in the tidy old picture, were meant to be a small central detail, a heavy anchor, but still a minor fraction of the whole. Here was one that seemed to dominate its galaxy, a tail large enough to wag the entire dog. The measurement was debated, and later work would revise and argue over the exact figure, which is exactly how science is supposed to work. But the shock of that first number did its job. It told us the ceiling might not be where we thought. Then there was the object called TON 618. This one is not a nearby galaxy whose centre we peer into. It is a quasar, which is what we call the blazing core of a galaxy in the distant past, lit up by a black hole that is actively feeding. TON 618 sits more than 10 billion light-years away, which means we're seeing it as it was when the universe was young, and the black hole powering it was estimated at around 66 billion times the mass of the Sun. 66 billion. If 17 billion was a crack in the ceiling, 66 billion was a hole punched clean through it. Here was a black hole many times heavier than anything the old picture allowed, and it was not sitting quietly in the present-day universe, where it might have had all the time in the world to grow. It was blazing away in the early universe, already gigantic when the cosmos itself was still young. There is a reason a distant quasar like TON 618 makes such a sharp point, and it comes back to that idea of looking into the past. Because it lies more than 10 billion light-years away, the light we see from it left when the universe was young, only a few billion years after the beginning. So we are not looking at a black hole that has had the full age of the cosmos to grow. We are looking at one that was already among the heaviest objects imaginable when the universe itself was still in its early years. That compresses the timing problem to its most severe form. A gigantic black hole in the present-day universe is a puzzle, but at least it has had all of cosmic history to reach its size. A gigantic black hole in the early universe has had almost no time at all, and yet there it is, already blazing at tens of billions of solar masses. These early giants are the sharpest version of the question that Phoenix A will pose in its own way. The question of how the universe managed to build its largest objects so quickly, faster than our patient, step-by-step story of growth seems to allow. These objects, and others like them that kept turning up, forced astronomers to do something they do not do lightly. They had to invent a new word. The two families, stellar mass and supermassive, no longer covered the range of what was out there. Above the supermassive black holes, above the few billion solar mass giants that had been the assumed ceiling, there was now a new tier, and it needed a name. The name that stuck was ultramassive. An ultramassive black hole is one above roughly 10 billion times the mass of the Sun, maybe higher, maybe much higher. The upper edge of the category was, and still is, genuinely unclear, because every time we think we have found the largest one, the possibility remains that there is a larger one we simply have not caught in the act. I want you to sit with what just happened in the history of this idea, because it is a pattern that repeats over and over in astronomy, and it is one of the quietly humbling things about looking at the universe. We drew a ceiling. We had good reasons for the ceiling, and then we looked a little harder and found that the ceiling was not the top of anything. It was just the top of our attention. Above it was a whole population of objects that had been there all along, waiting, while we told ourselves the story that nothing lived up there. The universe did not change when we found the ultramassive black holes. Only our sense of its limits did. The monsters were always there. We simply had not been looking in the right way to see them. I want to be fair to how science actually handled these first shocking numbers, because the story is not that astronomers simply accepted them and moved on. The original estimate for the black hole in NGC 1277, that figure as high as 17 billion solar masses, was challenged almost immediately. Other groups re-examined the galaxy, used different methods, made different assumptions, and some of them came back with substantially smaller numbers. The debate over exactly how heavy that particular black hole is has gone on for years and is not fully settled even now. And this is not a weakness in the story. It is the story working the way it should. An extraordinary measurement gets tested and retested and argued over, and slowly the community converges on what is real and what was an artifact of the method. But here is the thing that survived all the arguing, and it is the part that matters. Even after the most aggressive downward revisions, even granting every objection, what remained was a population of central black holes far heavier than the old ceiling allowed. The exact figure for any single object might slide up or down by a factor of 2 or 3 as the measurements improved. What did not go away was the category. Above the supermassive black holes, above the assumed top of the world, there really were objects in a heavier class, and no amount of careful re-examination made them fit back inside the tidy old picture. The individual numbers were uncertain. The existence of the new tier was not. And that is a crucial distinction to carry into the rest of this story, because Phoenix A lives at the very top of that uncertain, undeniable new tier, where the numbers are the shakiest and the objects are the most real. And notice something else about these first cracks. The ultramassive black holes did not just violate our sense of how big black holes could be. They raised a harder question, one that would become the central problem of this entire story. How did they get so large? Ton 618, blazing at 66 billion solar masses when the universe was still young, had a timing problem. It had not had enough time. The universe was not old enough to have grown something that heavy by the slow, patient, self-limiting process we thought we understood. So either these objects formed in some way we did not yet grasp, or they started out far larger than any dead star could ever leave behind. Either answer meant that our story about how the largest black holes come to be was missing something important. That question was already sitting on the table when the next object arrived, and this one did not announce itself through the motion of stars or the blaze of a quasar. It announced itself in the faintest light in the universe, the light left over from the birth of everything, and the way we found it is one of the strangest detection stories in modern astronomy. Part 4. A Shadow on the Big Bang's Light. In the year 2010, there was a telescope at the bottom of the world that was not looking for black holes at all. The South Pole Telescope sits on the high Antarctic ice, in some of the driest, stillest, coldest air on the planet, and it was built for one of the most delicate tasks in all of science. It was built to map the oldest light there is, the faint microwave glow that fills the entire sky, the radiation left over from the moment the universe first became transparent, not long after the Big Bang. This relic light is almost perfectly smooth in every direction, and the whole point of an instrument like the South Pole Telescope is to measure the tiny variations in it, the faint warm and cool patches that carry the fingerprints of the early cosmos. It is a machine for reading the universe's baby photograph. Now here is the thing that makes what happened next so strange. When that ancient light travels across billions of years of space to reach us, it does not always arrive untouched. Sometimes, on its way, it passes through an enormous reservoir of hot gas, and when it does, the gas leaves a mark. The relic light and the hot gas interact, and the light comes out the other side subtly changed, its pattern distorted in a very particular and recognizable way. So a telescope hunting for the smooth glow of the early universe will occasionally catch, printed over that glow, the shadow of something in the foreground, a distortion. A place where the oldest light in existence has been bent by something enormous standing between us and the dawn. That is what the South Pole Telescope saw. A distortion in the relic radiation, a signature that meant, unmistakably, that a huge amount of hot gas was sitting out there in that direction, gas heated to the point where it presses its fingerprint onto the light of the Big Bang itself. And so, the strangest fact in this entire story is already here, right at the beginning. The largest black hole we have ever found did not announce itself with a blaze of light or a scream of gravity. It announced itself as a shadow cast on the afterglow of creation. Let me take you into that moment, because I think it deserves to be felt rather than just described. Picture the control room, or the data as it comes down from the ice. The team is not looking for a monster. They are combing through maps of the microwave sky, chasing the faint temperature ripples that carry information about the beginning of the universe. And in one patch of sky, there is a smudge that should not be there, a distortion in the smooth ancient light, the telltale mark of an enormous mass of hot gas standing between the telescope and the edge of time. At first it is just a candidate, one signal among many, a place worth a second look. The follow-up begins. Optical telescopes turn toward that patch of sky, and the images come back crowded with galaxies, a whole swarm of them, gathered together where the distortion said mass should be. X-ray observatories look next, the instruments that see the hottest, most violent gas in the universe, and the readings climb and do not stop climbing until it becomes clear that this is one of the brightest sources of its kind ever recorded at those wavelengths. Radio dishes trace jets and cooler streams of matter threading through the whole structure, and slowly, across weeks and months of gathering evidence, the recognition settles over the people doing the work. They went looking for the faint music of the early universe, and they stumbled onto one of the most massive structures anywhere in the known cosmos. It was hiding in plain sight, written as a shadow on the light they were actually trying to read. Think about the odds that had to line up for this to work at all. The South Pole telescope can only do what it does because of where it sits. The air above the Antarctic plateau is among the driest and stillest on Earth, and dryness matters enormously for this kind of observation, because water vapour in the atmosphere absorbs exactly the wavelengths of light the telescope is trying to read. Almost anywhere else on the planet, the faint signal from the early universe would be smeared and swallowed by the moisture in the air, so the instrument had to be carried to the bottom of the world, to one of the harshest and most remote places a person can work, precisely so that it could sit under the clearest possible window onto the oldest light there is. And it was from that window, in that brutal cold, that the shadow of Phoenix first appeared. There is something almost poetic in the chain of it. To find one of the most massive objects in the universe, 5.7 billion light-years away, we first had to find the one patch of sky on Earth clear enough to see the faint mark it left, and that patch happened to be above the ice at the southern pole. I dwell on this because it underlines a theme that runs through the whole story of Phoenix A. We did not find it because it was easy to find. We found it through a long chain of demanding, precise, almost improbable steps, the right instrument in the right impossibly clear place, catching the gentlest of signals, followed up by a coordinated effort across every kind of telescope we have. And even after all of that, what we found was an object we still cannot fully explain. That gap between the enormous effort it took to see it and the incompleteness of our understanding once we had is, in a way, the emotional shape of the entire subject. We reached hard, across billions of light years, and what we grasped turned out to be stranger and larger than the framework we reached with. They named it the Phoenix Cluster, after the southern constellation in which it appears. It is a name that turned out to fit better than a name has any right to, because the phoenix is the bird that burns and is reborn, and this is a cluster defined by rebirth, by a centre that has caught fire again after ages of dark. When the team added up everything the cluster contained, all its galaxies, all its gas, all its unseen matter, they arrived at that staggering total of around 2 quadrillion times the mass of the Sun. And the cluster was not just massive, it was the brightest X-ray source of its kind ever recorded, blazing in that high energy light because the gas at its centre was doing something that gas in most clusters does not do. We will come to what that something is, because it is the key to the whole mystery. For now, hold on to the sheer improbability of the discovery. The most extreme galaxy cluster we had ever found, and one of the most massive black holes in existence, revealed themselves through the gentlest possible signal, a faint smudge on the oldest light in the universe. There is something worth noticing in how this happened, a lesson that runs underneath the facts. We did not find Phoenix A because we went looking for it. We found it because its host cluster happened to be doing something dramatic enough to leave a mark on the background light, and because we happened to have built an instrument sensitive enough to notice the mark. If the cluster had been a little quieter, a little more ordinary in its behaviour, it would have gone on sitting there, 5.7 billion light-years away, holding one of the largest black holes ever formed, and we would have had no idea. That thought is going to matter a great deal by the end of this video because it opens a door onto a much larger and much darker possibility. If we only found this one by luck, by catching it in the act of doing something loud, then how many others are out there sitting in silence, giving off no such signal, invisible to us precisely because they have gone quiet? Hold that question. We will open it fully near the end. It is worth dwelling for a moment on why the discovery method is so fitting, because there is a genuine physical elegance to it that goes beyond coincidence. The distortion the South Pole telescope detected has a name. It comes from an effect in which the ancient light of the Big Bang, passing through a cloud of extremely hot gas, gets a small energy boost from collisions with the fast-moving particles in that gas. The relic light comes out the other side slightly reshaped, its spectrum shifted in a characteristic pattern that is unmistakable once you know to look for it. And the beautiful part is this. The effect does not depend on how far away the gas is. Whether the hot cloud is nearby or halfway across the observable universe, the distortion it imprints on the background light is the same. That means this method can find massive clusters at enormous distances, clusters so remote that they would be faint and easy to miss in ordinary images, simply because they cast their shadow on a light that fills the entire sky. It is a way of finding the most massive structures in the universe by the marks they leave on the oldest light there is. There is also something worth appreciating in the sheer effort behind the follow-up, because a single distortion in the background light does not, by itself, tell you that you have found a monster. It tells you there is hot gas. Everything else, the galaxies, the X-ray brilliance, the black hole at the center, had to be assembled from a coordinated campaign across many different kinds of telescope, each seeing a different piece of the truth. The optical telescopes counted the galaxies and measured their distance. The X-ray observatories weighed the hot gas and revealed just how furiously it was glowing. The radio dishes traced the jets and the cooler streams of matter. No single instrument saw the whole thing. The Phoenix cluster only came into focus when all of those separate views were laid over one another, and the combined picture showed something none of them could have shown alone. It is a reminder that the biggest discoveries in modern astronomy are rarely a single glance through a single eyepiece. They are a mosaic, assembled patiently, out of many different ways of seeing. But first we have to confront the size. I have been throwing numbers at you, 100 billion solar masses, 25,000 times our own galaxy's black hole, and numbers like that slide off the mind because the mind has nothing to catch them on. So let me stop giving you masses for a moment and start giving you distances, because when you translate the mass of Phoenix A into a size you can try to walk across, something happens. The number stops being a number. It becomes a place. And once it becomes a place, the word black hole, the small dark point you have been picturing this whole time, quietly stops being able to describe it. Part 5. When a size stops being a size. To understand the size of Phoenix A, you first need one simple fact about black holes, and it is a fact that works in our favour because it is easy to hold. The size of a black hole scales directly with its mass. Double the mass, and you double the radius of the boundary around it, the event horizon, the surface of no return. There is no complicated curve here, no acceleration or falling off. It is a straight line. Twice as heavy means twice as wide. That simple rule is about to take the mass of Phoenix A and turn it into a distance, and the distance is where the horror lives. Let me build it up in steps, starting with something familiar. Take our own sun. The sun is not a black hole and never will be. It is not massive enough, but imagine for a moment that you could crush it down until it became one. All of that mass, all that fire, all that hundreds of thousands of miles of glowing plasma squeezed until it vanished behind an event horizon. How big would that horizon be? The answer is startlingly small, less than 4 meters across. You could stand in a room with the crushed-down sun, and it would be smaller than the room. The entire mass of the star that lights our sky, gives us our seasons, holds every planet in its orbit, would hide behind a boundary you could nearly reach around with your arms. That is what a black hole of one solar mass looks like as a size. A few meters. Tiny. Now climb up to our own galaxy's black hole, Sagittarius A star, at 4 million solar masses. 4 million times the Sun. Its event horizon is about 15 million miles across. That sounds enormous, and by human standards it is, but hold it against the scale of the solar system and it shrinks again. 15 million miles is small enough to fit comfortably inside the orbit of Mercury, the innermost planet. The black hole that anchors all 200 billion stars of the Milky Way would, if you dropped it into our solar system, sit tucked inside the path of the closest planet to the Sun, with room to spare. Big, undeniably. But our solar system would still swallow it whole and barely notice. And now, Phoenix A. Hold the straight line rule in your mind, double the mass and you double the size, and follow it all the way up to 100 billion solar masses. The event horizon of Phoenix A at the upper end of the estimates would reach about 180 billion miles from its center to its edge. From one side to the other, straight across, that is a diameter of roughly 370 billion miles. I know that is just another number, so let me anchor it to something. The distance from the Sun out to Pluto, all the way across our planetary system, out past the orbit of every planet, is a distance we struggle to picture already. The event horizon of Phoenix A is about 100 times wider than that. You could line up 100 copies of our entire solar system, edge to edge, and only then would you have spanned this one black hole. Let me try to make that unspeakable width real with the 2 fastest things we know, one from nature and one from ourselves. Light is the fastest thing in the universe. Nothing outruns it. Light crosses the distance from the Sun to the Earth in about 8 minutes, and it crosses the entire width of our solar system in a matter of hours. To cross the event horizon of Phoenix A from one edge to the other, light would need about 3 weeks. 3 weeks for the fastest thing that exists just to traverse the boundary of a single black hole. And if you wanted something built by human hands, picture a passenger jet, a Boeing 747 at its cruising speed, the kind of aircraft that crosses an ocean in a handful of hours. To fly the width of Phoenix A's event horizon, that jet would need over 70,000 years. 70,000 years of continuous flight, longer than our species has had recorded anything, just to get from one side of the boundary to the other. This is the moment I want you to feel the word failing. We've been saying black hole this whole time, and the phrase carries that mental image of a small dark point, a drain, a dot. But there is nothing dot-like about a region so wide that light takes 3 weeks to cross it. This is not an object in any sense that the word object usually carries. It is closer to a territory. It is a region of space, larger than a small star cluster, fenced off from the rest of reality by a boundary that light itself needs 3 weeks to span. When you cross into an ordinary black hole, you are falling into a thing. When you cross into Phoenix A, you are entering a place. And I think that shift, from thing to place, from object to territory, is the single most important reframing in this entire story. It is why the question on the thumbnail is not a gimmick, not a black hole, not because it fails to be one in the technical sense, but because the word can no longer carry the weight of what it is describing. There is a wrinkle here that most popular accounts skip over, and it makes the territory idea even stranger. You might assume that a black hole this monstrous would be the most violent, most destructive object imaginable, that the gravity at its edge would be so ferocious it would rip apart anything that came near. For a small black hole, that is exactly right. Near a stellar mass black hole, the gravity changes so sharply over even a short distance that an object falling in feels its near side pulled far harder than its far side, and it gets stretched out into a long thin stream, a process astronomers have actually named spaghettification, because that is what it looks like. Fall toward a small black hole, and you are drawn out into a strand of matter long before you ever reach the centre. But Phoenix A is so large that this does not happen at its boundary. The gravity is still overwhelming in total, but because the event horizon is so enormously far from the centre, the difference in pull between your head and your feet as you crossed it would be gentle. The tidal forces at the edge of Phoenix A are mild, counterintuitive but true, and it follows directly from the size. You could, in principle, drift across the event horizon of this black hole without feeling a single jolt, no stretching, no tearing, no sensation of a boundary at all. You would pass the surface of no return and feel nothing change. You would not know you had crossed it. You would not even know you were doomed. Sit with that for a moment because it inverts everything the word black hole is supposed to make you feel. The terror we attach to these objects is a terror of violence, of being torn apart. Phoenix A offers no violence at its edge. It offers only a quiet, invisible line, and the fact that once you have crossed it, the death is still coming, just later, somewhere down inside, hours or days after you slipped past a boundary you never saw and never felt. That is what makes ultramassive black holes feel less like predators and more like empires. A predator lunges. An empire simply extends its border around you while you're looking the other way, and one day you realize you have been inside it all along, and there was never a moment where you could point to the line and say, there, that was where I was still free. Let me linger on that straight line rule a little longer, because it has a consequence that most people find surprising, and that makes the size of Phoenix A even harder to fit into the usual picture of a black hole. Because the radius grows in direct step with the mass, but the volume enclosed by that radius grows far faster, something strange happens to the density of a black hole as it gets larger. The biggest black holes are, in a certain sense, not dense at all. If you took the total mass of Phoenix A and spread it across the enormous volume inside its event horizon, the average density would be shockingly low, lower than air, in some reckonings approaching the thinness of the near vacuum of space itself. The image of a black hole as a point of unimaginable compression, everything crushed into a tiny dense speck, is true for small black holes and becomes less and less true the larger they grow. Phoenix A is not a dense speck. It is a colossal region of space whose average density, spread across its whole immense interior, is barely anything at all. The compression, whatever happens to the matter, is hidden far down at the centre. The territory as a whole is mostly emptiness bounded by an unimaginable edge. I find that inversion genuinely difficult to hold, and I think it is worth sitting with, because it upends the intuition at the root of the word. We picture black holes as the densest things imaginable, and for the small ones that is correct. But scale them up, and the density falls until the largest ones are, on average, among the least dense large objects in the universe, immense low-density regions defined not by how tightly their matter is packed, but simply by how much space their boundary encloses. Phoenix A is a case where nearly every instinct the phrase black hole gives you points the wrong way. It is not small. It is not on average dense. It is not violent at its edge. It is enormous and diffuse and gentle at its border, and lethal only in the quiet, patient way that a territory is lethal, by surrounding you before you know it is there. So this is the size we're dealing with. Not a point, not a dot. A region 100 times wider than our solar system, bounded by a surface light takes 3 weeks to cross, whose edge is so gentle it would let you enter without a whisper. Keep the territory in your mind, because we're about to walk right up to its border and step across it slowly, so that you can feel exactly what it would be like to be swallowed by something this patient. Part 6. The Gentle Death. Let me take you across the boundary, slowly, the way it would actually happen, because I think the experience of falling into Phoenix A tells you more about what it is than any number could. Imagine you are drifting toward it, pulled in equal measure by gravity and by curiosity. For a very long time, nothing changes. This is the first thing that would surprise you, if you were the kind of traveller who expected drama. There is no roar, no shudder, no growing sense of violence. Phoenix A is so large that the region around it is calm. The pull builds, but it builds slowly, patiently, the way a tide comes in rather than the way a wave breaks. You have time. You have in fact a great deal of time, and that is part of what makes it terrible. As you fall, the light from the rest of the universe begins to gather. Behind you, the stars and galaxies you are leaving crowd together, their light bending as it follows the curve of space around this immense mass. What was once a whole sky spread out in every direction slowly draws in toward a single bright circle behind you, a shrinking window onto everything you came from. The stars within that window shift in colour. They redden, their light stretched by the deepening gravity, and they crowd closer together, tightening into a ring, a bright band closing like an aperture. There is no wall ahead of you. There is no marker, no line drawn in space, no sign that says this is the edge. There is only the slow gathering of the outside universe into a smaller and smaller circle at your back, and the strange, calm absence of anything happening in front of you. And then, at some moment you cannot identify, you cross the event horizon. Nothing marks it. You feel no jolt, no boundary, no change in your body or your senses, but something has changed, absolutely and forever. You have passed a line that no longer lets you send any signal back to the universe you left. If you tried to shout, to flash a light, to reach back toward that shrinking bright circle, none of it would ever arrive. The line you just drifted across is the line beyond which the outside universe can no longer receive anything from you, and cannot ever again. You are still alive, you're still thinking, you still feel entirely intact, and you are already, in every sense that matters to the world you came from, gone. The universe has forgotten you instantly, not because anything happened to you, but because the information about you can no longer escape. You would not know you had crossed it. You would not even know you were doomed. The death, when it comes later. It comes somewhere down inside, hours or days after you slipped past a boundary you never saw, as the tidal forces finally sharpen near the centre, and the calm falling gives way at last to the tearing that a small black hole would have done to you at the very start. But that is far in your future, from the moment you cross. For a long stretch of your remaining time, you simply fall, intact and aware, through the inside of a region larger than 100 solar systems, with the last light of everything you ever knew closed into a fading point behind you. I want to stop here, because I think this is the emotional centre of what Phoenix A is, and it is worth naming plainly. The most disturbing thing about this object is not its violence, it is the absence of its violence. We are used to imagining catastrophe as something loud and sharp, a moment you could point to, a boundary you would feel yourself hit. Near a small black hole, that is exactly the death you would get, a scream of tidal force, a clear and terrible instant. Phoenix A offers none of that at its edge. It offers a quiet, invisible line that you drift across in perfect comfort, feeling nothing, knowing nothing, already lost. The doom is not a wall you strike, it is a border you wander past without noticing, and somehow that is worse than any wall, because a wall at least gives you a moment of knowing. Phoenix A takes even that away. It lets you keep every sensation of freedom right up until the freedom means nothing. And here is the part that I find genuinely hard to shake. The reason this matters beyond a thought experiment. This is not just how it would feel to fall into a black hole. This is a picture of how the largest structures in the universe actually operate. They do not announce themselves. They do not warn. They extend their reach around things quietly, on timescales so long and forces so gentle that from the inside there is no clear moment of capture. The territory idea from a moment ago becomes real here. An empire this size does not need to lunge. It only needs to be and to wait, and to let the things around it drift slowly inward across a border none of them can feel. Now, I have been describing this as though you could actually make the journey, and of course you never could. Nothing you could build could reach Phoenix A, and if it did, you would have crossed 5.7 billion light-years to be quietly erased. But the impossibility of the trip is not the point. The point is what the trip reveals about the nature of the thing. A small black hole is an event, a violent instant. Phoenix A is a condition, a place, a slow and patient region of space that changes the rules for everything that comes near it and asks for nothing in return, not even your awareness of what is happening to you. When you picture it now, I hope the small dark dot is gone for good, replaced by something quieter and far larger, a border in space that you could cross without a whisper. There is a detail in that slow fall that I skipped past, and it deserves its own moment, because it is one of the strangest features of crossing into any black hole, and it becomes almost unbearable at this scale. As you approach the boundary, time itself, from the point of view of the outside universe, begins to stretch for you. Seen from far away, a clock falling toward a black hole appears to tick more and more slowly the closer it gets to the edge, until, right at the boundary, it appears to nearly stop. To someone watching you fall into Phoenix A from a safe distance, you would never quite seem to cross. You would appear to slow and redden and freeze, hanging at the edge, your image fading but never fully arriving, held forever at the threshold. And yet from your own point of view, nothing of the kind happens. You feel time passing normally. You drift across the boundary in your own steady present, feeling no pause, no freezing, no threshold at all. Two utterly different truths about the same event, depending only on where you stand. That split is not a trick of perception. It is how gravity actually shapes time, and it means that the moment of crossing is a moment that different observers can never agree on. The universe outside sees you frozen at the edge for the rest of its existence. You see yourself fall smoothly through and onward toward the center. There is no single answer to the question of when you crossed, because time near an object this massive is not the shared, universal thing our daily lives assume it to be. And I raise it here not to add a technical flourish, but because it deepens the quiet horror of the gentle death. Not only do you feel no boundary as you cross, there is not even a single agreed-upon instant at which the crossing happened. The line you drift over is not just invisible. It is, in a real sense, in a different place in time for you than for everyone watching. The border of Phoenix A is not only silent, it is a place where the very idea of a shared moment comes apart. But all of this only deepens the real mystery, the one that has been waiting underneath every number I have given you. We have talked about how big Phoenix A is and what it would be like to fall into it. We have not yet talked about the question that keeps astronomers genuinely unsettled, the one they cannot answer with any confidence. How did something this large ever come to exist in the first place? Because when you do the arithmetic, when you take the ordinary story of how black holes grow and try to build one this heavy, the story does not work. There has not been enough time, not since the beginning of the universe itself. Let me show you exactly where the math breaks, because that is where Phoenix A stops being merely enormous and starts being something that should not, by our own rules, be here at all. Part 7. It has no business being here. Here is the standard story of how a supermassive black hole comes to be, the one we tell in the textbooks, and I want to walk through it carefully so you can see exactly where it starts to strain under the weight of Phoenix A. It begins with a seed. Somewhere in the early universe, a black hole forms, perhaps from the death of an enormous early star, leaving behind an object of a few dozen or a few hundred times the mass of the Sun. This seed sits in a young galaxy full of gas, and it begins to eat. Gas spirals in, the black hole grows, and over time it also merges with other black holes when its galaxy collides and combines with neighbouring galaxies, as galaxies do across the long history of the cosmos. Feeding and merging over billions of years, the seed inflates from a stellar-sized object into a giant of 1,000,000, then 100,000,000, then perhaps 1,000,000,000 times the mass of the Sun. It is slow, it is patient, it takes most of the age of the universe, but it works. For the ordinary supermassive black holes at the centres of most galaxies, this story holds together, though I will be honest with you, even for those it holds together only barely, with the timing stretched about as tight as it will go. Now try to build Phoenix A this way. Try to take a modest seed and grow it by feeding and merging all the way up to 100 billion times the mass of the Sun. And the story does not merely strain, it breaks. The problem is time, and there is a hard ceiling on how much of it there is. The universe is 13.8 billion years old. That is the entire runway. Everything that has ever formed, every star, every galaxy, every black hole, had to do so within that span, because before it there was simply no universe to form in. So whatever built Phoenix A had, at most, 13.8 billion years to work with, and in practice much less, because the black hole could not start growing until there was gas and structure for it to grow from, which took time to appear after the beginning. Against that fixed runway, set the speed limit I described earlier, the one built into the physics of feeding. A black hole cannot eat arbitrarily fast. As gas falls in and heats up and glows, the outward pressure of that glow pushes back against the incoming gas, and past a certain rate the pushing out balances the falling in, and the black hole chokes off its own supply. This is a real physical ceiling on how quickly any black hole can grow, and it means that even a black hole floating in an ocean of food can only consume it so fast. To grow a black hole of 100 billion solar masses through ordinary feeding, you would need it to eat at very close to that maximum theoretical rate, continuously, without pause, for almost the entire history of the universe, not in bursts, not with breaks. Continuously, at nearly the fastest rate physics allows, for something like 13 billion years straight. And that simply does not happen in reality. Real black holes do not feed steadily at their maximum rate for billions of years. They burp, they choke, they exhaust the gas in their immediate surroundings and then sit hungry, waiting for more to arrive. They throttle themselves through exactly the radiation pressure I described, flaring bright, pushing their own food away, then dimming and waiting for the pushed-away gas to settle back. The real history of any black hole is not a smooth, uninterrupted feast. It is a stop-and-start affair, full of long fasts and short meals, and a stop-and-start feeder cannot reach 100 billion solar masses in the time available. The math does not close. There are not enough years, and the feeding is not efficient enough to build something this large by the ordinary route. So we are left with a genuinely uncomfortable conclusion, and I want to state it as plainly as the astronomers who study this do. By the rules we currently understand, Phoenix A should not exist. It is too large to have been built by the process we thought builds these objects in the time the universe has been around. And when a thing exists that our rules say should not, there are only two honest possibilities. Either it formed through some process we do not yet understand, something outside the ordinary story of seeds and slow feeding. Or it did not start small at all. It began enormous, far larger than any dead star could ever leave behind, and merely grew larger from an already staggering starting point. I find this one of the most quietly vertiginous ideas in all of astronomy, and it is worth pausing on. We are not looking at an object that stretches our theories. We are looking at an object that our theories, taken at face value, forbid. And yet there it is, 5.7 billion light-years away, weighing whatever it weighs, entirely indifferent to the fact that our best account of how it could have formed does not add up. The universe is under no obligation to build only the things our equations permit on the timescales our equations prefer. It built Phoenix A. The failure is not in the object. The failure is in our story about how such objects come to be. And that is a very different and much more humbling place to stand than simply being impressed by something large. This is the deeper meaning of the title. The more scientists look at Phoenix A, the scarier it gets, and the fear is not that it might harm us. The fear is intellectual, the specific vertigo of watching a confident explanation fall short in front of you. We can measure the object, we can weigh it, size it, describe how it would swallow you. What we cannot do, with any real confidence, is tell you how it got here. And an object we can measure but cannot explain is a more unsettling thing than an object we simply cannot see, because it means the gap is not in our instruments, the gap is in our understanding. Let me put some real arithmetic behind the timing problem, because the numbers make the impossibility concrete in a way that the general description does not. That self-imposed speed limit on how fast a black hole can grow translates, roughly, into a doubling time. Feeding at its maximum sustainable rate, a black hole can double its mass only every so many tens of millions of years, and no faster, because past that rate it chokes on its own light. Now think about what it takes to get from a modest seed to 100 billion solar masses by doubling. Start at 100 solar masses and you need to double again and again, something like 30 times over, just to reach the 100 billion mark. Each doubling takes its minimum stretch of time, and 30 of them, back to back, with no pauses, no fasting, no interruptions, consumes very nearly the entire age of the universe. There is no slack. There is no room for the black hole to ever stop eating, not even once, not even for the long dry spells that every real black hole endures. And that is the crux of why the story fails, because real black holes stop eating all the time. We know they do because Phoenix A itself spent most of its life dormant, which is the very thing that makes it remarkable. A black hole cannot both have grown to 100 billion solar masses by feeding continuously at its maximum rate for the whole age of the universe, and also have spent hundreds of millions of years asleep. Those two facts contradict each other. The continuous feeding the growth requires leaves no time for the long dormancy we know these giants experience. So the ordinary picture does not merely run short on time by a little. It demands a kind of behavior, unbroken maximum feeding across all of cosmic history, that we know for a fact these objects do not exhibit. The arithmetic and the observations point the same way. Something other than slow, patient, ordinary growth had to be involved. The monster was not assembled the way we assemble the merely large. So if the ordinary story does not work, what is the alternative? If Phoenix A could not have grown slowly from a small seed, then how did it come to be? Astronomers have ideas, and they are strange ideas, involving the very earliest moments of the universe, gas clouds collapsing directly into giants without ever becoming stars, and entire clusters of galaxies slamming together and funneling their separate monsters into one. Let me show you where the largest black holes may actually come from, because the leading answers do not make Phoenix A more ordinary. They make its origins even stranger than its size. Part 8. Where the monsters come from. The first idea is that the seed was never small to begin with. Instead of starting as the corpse of a single dead star, a few dozen times the mass of the Sun, the seed of an ultramassive black hole may have formed directly, from a cloud of gas in the early universe that skipped the stellar stage entirely and collapsed straight into a black hole. To see why that matters, you have to understand what usually happens to a large cloud of gas. Normally, a giant cloud in a young galaxy does not collapse all at once. It fragments. It breaks into many smaller pieces, and each piece condenses into a star, and you end up with a cluster of stars rather than a single object. Stars are what gas clouds make, almost always, because as a piece of the cloud contracts, it heats up and begins to shine, and that resists further collapse, and the whole thing settles into the familiar business of forming suns. But in certain rare conditions in the early universe, a cloud might have been able to avoid fragmenting. If it stayed hot and smooth and did not break into pieces, it could have collapsed as a single unit, all of that mass falling together without ever lighting up as stars, straight down into a black hole in one motion. A black hole born this way, from what we call direct collapse, would not start at a few dozen solar masses. It could start at tens of thousands of times the mass of the Sun, already, on the day it formed. And that changes everything about the timing problem. A seed 10,000 or 100,000 times heavier than a stellar corpse has a colossal head start. It does not have to spend the first stretch of cosmic history slowly climbing out of the lightweight range. It begins already massive, and has all the remaining time to grow larger still. Give a black hole a head start that large, and the runway of 13.8 billion years starts to look a little less impossibly short. Not comfortable, but less impossible. The direct collapse idea is, in essence, a way of saying that maybe the monsters were born as monsters and never had to work their way up. The second idea is even grander in scale. and it fits Phoenix A in a particular way because of where it lives. Remember that Phoenix A does not sit at the centre of a single galaxy. It sits at the centre of an entire cluster of galaxies, one of the most massive structures in the universe. And clusters like that are not built in a single step. They assemble over cosmic time as smaller groups of galaxies fall together and merge into larger ones, and those merge into larger ones still. When entire clusters slam together in the early universe, they bring with them all of their separate central black holes, each galaxy carrying its own supermassive giant at its core. Those black holes can sink toward the centre of the newly combined structure, drawn down into the deepest part of the shared gravitational well, and there, over time, they can merge with one another. Picture that for a moment. Not one black hole growing by sipping gas, but many already enormous black holes, the central engines of many separate galaxies, all funneled into the same place and combined into a single object. This is assembly by collision rather than by patient eating. It is a way of reaching 100 billion solar masses, not by growing one seed for the whole age of the universe, but by gathering together giants that each grew separately and then fusing them at the bottom of a cluster-sized gravitational well. For an object sitting where Phoenix A sits, at the centre of one of the most massive clusters we know, this route has a certain natural logic. The very environment that makes the cluster extreme is also the environment most capable of concentrating multiple giants into one. It is worth noticing that these two origin stories are not actually rivals, and that the truth for Phoenix A may well involve both. A black hole could begin as a direct collapse seed, born already massive in the clean gas of the early universe, and then grow further not only by feeding but by merging, again and again, as its galaxy and then its cluster assembled around it. The head start and the collisions could work together, the large seed giving it a base to build from, and the cluster environment funneling other giants into it over billions of years. In that combined picture, Phoenix A is the end product of nearly every mass-gathering process the universe has to offer, all of them stacked one on top of another, an object that used every available route to reach the size it has. That may be exactly what it takes to build something at the very top of the scale. Not one extraordinary process, but all of the ordinary and extraordinary ones at once, concentrated in a single place with a history perfectly suited to gathering mass. That possibility also hints at why objects like Phoenix A are so rare. To reach the extreme upper end, you may need a specific and unlikely sequence of events, the right kind of seed forming in the right early conditions, landing in the right kind of galaxy, at the centre of the right kind of cluster, with the right history of mergers to feed it, all coming together in one location. Change any step and you get something merely large rather than something at the ceiling. The rarity of the largest black holes, then, would not be an accident but a consequence of how many things have to go right, or from a certain point of view go wrong for the universe to assemble one. Phoenix A may be rare precisely because it required the whole machinery of cosmic growth to align in its favour, and that alignment does not happen often. Both of these ideas, direct collapse and cluster scale merging, share something important, and I do not want it to slip past. Neither of them is a small adjustment to the standard story. Neither says, well, the black hole just fed a little faster than we thought. Both of them say that the ordinary picture, the modest seed growing slowly, is simply not how the largest black holes came to be. They require a different origin entirely, one rooted in the strangest and least understood epoch of cosmic history, the early universe when the first structures were violently assembling themselves out of the raw material of the Big Bang. To explain Phoenix A, in other words, we have to reach back to conditions we can barely model, and processes we have never directly observed, and even then we're not certain we have it right. That uncertainty is the honest core of this section, and I want to hold it up rather than paper over it. We do not know how Phoenix A formed. We have candidate stories, direct collapse seeds and cluster mergers, and they are serious, physically motivated ideas, not guesses. But we cannot yet point to Phoenix A and say, this is the road it took. The textbook account is wrong, or at least badly incomplete, and the replacements are still being worked out at the edges of what we can observe. When you look at this object, you are looking at something whose very existence is telling us that our understanding of how the biggest things in the universe get made has a hole in it, and the hole is exactly the size of a 100 billion solar mass black hole that our timeline says should not fit. There is a reason to think the direct collapse route was only ever possible very early, and it tells you something about how special the conditions had to be. The trick, remember, is to get a large cloud of gas to collapse as a single unit instead of fragmenting into a swarm of stars. What lets gas fragment is its ability to cool. As a piece of a cloud cools, it can contract and condense into a star, and this cooling is made easier by the presence of heavier elements, the carbon and oxygen and iron that stars themselves manufacture and scatter through the universe when they die. But in the very early universe, before many stars had lived and died, those heavier elements did not yet exist. The gas was almost pure hydrogen and helium pure hydrogen and helium cool poorly. A cloud that cannot cool efficiently cannot fragment easily, and a cloud that cannot fragment can collapse whole. So the window for direct collapse was open only in the young cosmos, before the first generations of stars had polluted the gas with the elements that would have caused it to break apart. The largest seeds could only be born in a universe still clean of the debris of earlier stars. It is a narrow early door, and it may be the door that some of the biggest black holes came through. The cluster merger route has its own kind of strangeness, and it involves a problem that is still not fully solved, sometimes called the final approach problem. When two black holes are drawn toward each other at the center of a merging system, they spiral inward, but as they get close, their inward drift can stall. They settle into a mutual orbit and then struggle to lose the last of their energy and actually merge, because there is nothing obvious left to carry that energy away. For two black holes to truly become one, something has to drain off the final momentum, whether the surrounding gas, the gravitational tug of passing stars, or the slow bleeding of energy into ripples in space-time itself. Whether and how this happens for the largest black holes, at the centers of the largest merging clusters, is a genuine open question. So even the assembly by collision route, which seems so natural for an object sitting at the center of a giant cluster, hides an unsolved piece. We can see that clusters merge. We can see that they bring their black holes together. Exactly how those black holes finish the job and fuse into a single ultramassive giant is still, in part, a mystery we are working to close. But strange as its origins are, the origin is not even the most active part of the mystery. Because whatever built Phoenix A finished its work long ago. The thing that makes this object a live puzzle, rather than a historical one, is what it is doing right now, in the present, in the light reaching us today. It is feeding. And to understand why that is so shocking, why an ultra-massive black hole eating hard is a genuine violation of what we expect, I need to tell you about a quiet, beautiful balance that governs almost every massive galaxy cluster in the universe. A balance that, in Phoenix, has broken. Part 9. The Broken Thermostat. To understand what Phoenix A is doing, you have to understand the environment it lives inside, because a black hole at the center of a cluster is not sitting in empty space. It is sitting in a sea. The space between the galaxies of a massive cluster is not truly empty. It is filled with gas, an enormous thin reservoir of it, stretching across millions of light years. This is not gas like the air you breathe. It is plasma, heated to tens of millions of degrees, so hot that it glows not in visible light but in X-rays, which is exactly why the Phoenix cluster shone so brightly when the X-ray observatories turned toward it. Picture the whole cluster as suspended in a faint, immense, invisible fog of gas so hot it would be lethal at any density, but so thin, so spread out, that at any single point it is nearly a vacuum. The mass of that gas, added up across the whole cluster, is staggering. It is one of the great hidden reservoirs of matter in the universe. Now, here is what that gas wants to do, left to itself. Hot gas radiates away its heat over time. It glows, and glowing costs energy, and so it slowly cools. And as gas cools, it loses the pressure that was holding it up, and it begins to fall inward under the cluster's gravity, sinking toward the center where the pull is strongest. As it falls and gathers at the center, it grows denser, and denser gas cools faster, and cooler gas falls faster still, in a runaway that should feed on itself. The end result, if nothing stopped it, would be an enormous flow of gas cooling and pooling at the very center of the cluster, condensing into new stars at a tremendous rate. Astronomers have a name for this expected process. They call it a cooling flow. And for a long time, the great puzzle was that we almost never saw it happen the way the theory said it should. Cluster after cluster, we looked at the centers where all that cooling gas should have been pooling and forming stars in a frenzy, and instead we found relative calm. The gas was there, hot as ever, but it was not cooling and collapsing into a storm of star formation. Something was holding the runaway in check. Something was keeping the gas hot, preventing it from pooling, stopping the flow before it could get started. For years, this was one of the real unsolved problems in the study of galaxy clusters. The gas should be cooling catastrophically, and it was not, and we did not fully understand why. The answer, when it came together, is one of the most elegant pieces of self-regulation in all of astrophysics, and the black hole is at the center of it. The supermassive black hole at a cluster's center acts like a thermostat. Follow the loop. Gas cools and begins to fall inward, exactly as the theory says. Some of that falling gas reaches the center and feeds the black hole. The feeding black hole responds by launching jets, tremendous beams of energy and particles blasting outward from its poles at nearly the speed of light. Those jets slam into the surrounding gas and reheat it, pumping energy back into the very reservoir that was trying to cool. The reheated gas stops falling, the flow shuts down, and with its food supply cut off, the black hole quiets again until the gas slowly begins to cool once more and the whole cycle repeats. It is a thermostat in the truest sense. When the gas cools too much, the black hole switches on and heats it back up. When the gas is hot enough, the black hole switches off. The loop holds the center of the cluster in a balance, letting stars form only at a modest, controlled rate, keeping the catastrophic cooling flow from ever running away. Across the universe, in cluster after cluster, this quiet feedback loop is running, a black hole and an ocean of gas holding each other in check, each responding to the other, a balance maintained over billions of years. It is the reason the centers of most clusters are calm. The thermostat works. In the Phoenix cluster, the thermostat is broken. That is the whole shock of this object, stated in 4 words, and everything else follows from it. In Phoenix, the balance has failed. The cooling gas is winning. The runaway that the thermostat is supposed to prevent is actually happening. Gas is cooling and pouring toward the center of the cluster, and the black hole, despite its size, despite its jets, despite everything it is doing, cannot reheat the gas fast enough to stop the flow. The safety mechanism that regulates every other cluster we know is in this one failing to hold. It is worth being precise about what winning means for the cooling gas, because it is not a small imbalance. In a normally regulated cluster, the amount of gas that manages to cool all the way down and form stars is a trickle, held in check by the black hole's reheating. In Phoenix, that trickle has become a flood, with the cooling proceeding at something close to the full runaway rate the old theory predicted, before we understood the thermostat at all. In other words, Phoenix looks like what every cluster was once expected to look like. Before we discovered that central black holes hold the cooling in check, it is the exception that shows us the rule by breaking it. A living example of the catastrophe that the feedback loop is supposed to prevent, running almost unopposed in a single place. To study Phoenix is to see what the calm centers of all the other clusters would become if their thermostats ever failed, and you can see the failure in the most direct way possible by looking at how fast the central galaxy is making stars. When the cooling flow runs unchecked, gas pools at the center and collapses into new stars in enormous numbers, and that is exactly what we see in Phoenix. The central galaxy of the cluster is forming new stars at a rate of somewhere around 700 to 1,000 times the mass of the Sun every single year. Let me give you the comparison that makes that number land. Our entire Milky Way galaxy, all 200 billion stars of it, forms new stars at a rate of about 1 solar mass per year. 1. The central galaxy of the Phoenix cluster is building stars close to 1,000 times faster than our entire galaxy does. It is a firestorm of creation, a galaxy caught in the act of the runaway cooling flow that almost every other cluster manages to suppress. I want you to picture what that would actually look like, because the number 700 to 1,000 is abstract, but the reality of it is not. Imagine a galaxy where new stars are igniting at hundreds of times the rate of anything in our neighborhood. A place where the sky, if you could stand under it, would be rewritten on the timescale of geology rather than the timescale of the cosmos. New suns flickering on across the heavens, fast enough that the constellations themselves would not be stable across the history of a world. A galaxy bathed in the light of an ongoing baby boom of stars, a wave of creation with no clear precedent and no clear ending in sight. That is the central galaxy of Phoenix. And it is not calm, and it is not balanced, and it is not supposed to be like this. It is a system where the regulator has fallen behind the thing it is meant to regulate. And in the middle of all that newborn fury, At the very center of the firestorm sits Phoenix A, not sleeping. Not quietly holding the cluster in balance the way a well-behaved central black hole should. It is feeding, hard, as the cooling flow pours matter down onto it faster than it can push back. Its jets are punching outward, we can see them. Tremendous beams carving cavities in the surrounding gas the size of small galaxies. But the jets are not winning. They are not strong enough to stop the inflow. The gas keeps coming. This is a black hole in the middle of a feeding event that has already been going on for at least tens of millions of years and may continue for hundreds of millions more. A giant that woke up to find a meal too large to handle gracefully, eating and still falling behind. We can actually see the fingerprints of this feedback loop written into the gas of other clusters, and it is one of the more satisfying confirmations in the field, so let me describe it. When the jets from a central black hole punch outward into the surrounding gas, they do not simply warm it uniformly, they blow bubbles. They carve out enormous cavities in the hot reservoir, pushing the gas aside and creating enormous hollow regions, sometimes large enough to hold an entire small galaxy inside them. And because the hot gas glows in X-rays, those cavities show up as dark voids in the X-ray images, holes in the glow where the jets have shoved the gas away. We can look at cluster after cluster and see these bubbles, some of them clearly older, drifting outward and fading, others fresh and close to the center, a record of past eruptions preserved in the gas like rings in a tree. It is direct visual evidence of the thermostat at work, the black hole periodically switching on, blowing its bubbles, reheating the gas, and switching off again, over and over across the history of the cluster. That evidence is exactly what makes Phoenix so remarkable by contrast. In a normally regulated cluster, the bubbles and cavities are enough. The reheating keeps pace with the cooling, and the center stays calm. In Phoenix, we still see the signs of the black hole trying. The jets are there, the cavities are there, the engine is running, but it is not enough. The cooling is outrunning the reheating anyway. It is not that the thermostat is absent or switched off. It is that the thermostat is present and active and doing everything it does in every other cluster and still losing. That is a different and more unsettling kind of failure than simple absence. It is the failure of a mechanism that works everywhere else, overwhelmed here by conditions that have tipped too far for it to correct. The regulator is not broken in the sense of being gone. It is broken in the sense of being outmatched. So when I told you at the very beginning that Phoenix A is awake, this is what awake means at this scale. It does not mean a brief flicker of activity. It means an active engine at the center of a galaxy, pouring out energy, driving jets, caught in a runaway that the rest of the universe has learned to prevent. Phoenix A is the exception to the great quiet balance of clusters, the one place where the thermostat has broken and the cooling gas is winning. And the natural question, the one astronomers keep circling back to, is simply, why here? Why did this cluster, out of all the massive clusters in the universe, fall out of the balance that holds all the others? What is different about Phoenix? The answer turns out to say something about the specific history of this one structure, and about a much older process we thought had ended long ago. Part 10. Why Phoenix stays awake. There are two leading explanations for why Phoenix, and seemingly Phoenix alone among the great clusters, has fallen out of the balance that holds the others, and they are not in competition. They may both be true at once, and together they paint a picture of a cluster with an unusual shape and an unusually quiet past. The first explanation is about the shape of the cluster, its structure. The Phoenix cluster is unusually compact for its mass. Most of its enormous matter is concentrated in a relatively small central region, rather than spread out broadly, and that concentration matters a great deal. When you pack that much mass into a tight center, you create a steep gravitational well, a place where the pull toward the middle is especially strong and especially sharp. Gas sitting in that well feels a fierce inward tug, and it is drawn toward the center faster than it would be in a more diffuse cluster. The steeper the well, the faster the gas falls, and the faster the gas falls, the harder it becomes for the black hole's jets to reheat it in time. A more spread-out cluster gives its central black hole a fighting chance to keep up. Phoenix, with its tight, concentrated core, funnels gas toward the center faster than the thermostat can respond. The geometry of the cluster is stacked against the balance. The second explanation is about the history of the cluster, its past. Most massive clusters grow through a violent series of mergers, smaller groups of galaxies crashing together and combining over cosmic time. And every one of those mergers is disruptive. When clusters collide, they stir up the gas, they slosh it around, they inject energy and turbulence into the reservoir, and all of that churning tends to interrupt any runaway cooling before it can get going. A cluster that keeps getting hit keeps having its gas stirred, and stirred gas does not settle quietly into a cooling flow. But Phoenix appears to have avoided major mergers for a very long time, for billions of years. It has had a relatively quiet recent history, undisturbed, its gas left alone. And gas that is left alone, undisturbed, in a steep gravitational well, does exactly what the old cooling flow theory said it should. It settles, it cools, it falls. The very piece of the cluster's history is what allowed the runaway to begin. Put those two together and you get a coherent picture. Phoenix is compact enough to pull its gas inward hard, and calm enough in its recent past to let that gas settle and cool without interruption. The steep well and the quiet history working together tipped this one cluster out of the balance that its more disturbed, more diffuse cousins managed to maintain. Both explanations, notice, describe an absence rather than a presence. Neither one says that some extra force is actively driving Phoenix into its runaway. The steep gravitational well is not pushing the gas inward with any special violence, it is simply failing to hold it back gently. The quiet merger history is not adding energy. It is merely the lack of the disruptions that would have interrupted the cooling elsewhere. In both cases, what makes Phoenix extreme is not something extra being done to it, but something ordinary being left undone. The stirring that calms other clusters did not happen here. The spreading out that gives other central black holes a fighting chance did not happen here. Phoenix is not extraordinary because of what was added. It is extraordinary because of what was missing, the interruptions and the diffusion that keep every other cluster in balance. Sometimes the most dramatic outcome in nature comes not from a new force, but from the removal of the thing that was quietly keeping the peace. That is a subtle idea, and I think it is worth holding on to because it runs against our instincts. We tend to look for a cause that pushes, an active agent making the dramatic thing happen. But the drama in Phoenix comes from the failure of a restraint. It is the difference between a fire started by a spark and a fire that spread because no one was there to put it out. The gas in Phoenix was always going to want to cool and fall. In every other cluster, something intervenes. Here, nothing did for long enough, and the wanting became a torrent. The monster at the centre did not wake because something reached in and shook it. It woke because the gas around it was finally left alone long enough to come pouring down on its own. And by the time the black hole responded, the flood was already beyond what its jets could turn back. Whatever the exact mix of causes, the result is the same. We're watching something rare happen in slow motion, a galaxy cluster where the central black hole, for all its size and all its raw power, simply cannot keep up with the gas flowing toward it. A thermostat that has fallen behind, a monster that woke to find a meal too large to eat gracefully. But here is where this stops being a story about one unusual cluster, and becomes something stranger and larger. Because this runaway cooling, this catastrophic flow of gas onto a central black hole in a firestorm of star formation, is not just a curiosity of the present-day universe. It is exactly what astronomers think happened in the early universe, long ago, when the first supermassive black holes were assembling themselves for the very first time. In the young cosmos, before the great regulating balance had settled into place, gas would have poured onto growing black holes in just this kind of unchecked torrent, feeding them, building them, lighting up their galaxies with furious star formation. That process was supposed to be over. It belonged to the distant past, to the era of assembly, to conditions that no longer exist in the calm, balanced clusters of today. And yet in Phoenix it seems to be happening now. Or rather, it was happening 5.7 billion years ago, which is when the light we are receiving left the cluster. What we may be looking at when we look at Phoenix is a live view of an ancient process, a rerun of the early universe's black hole building playing out in a single cluster far more recently than it had any right to. The conditions that built the first monsters, thought to be long gone, reassembled themselves in this one place, and we happened to catch the light. It is as if a museum exhibit of an extinct process suddenly began operating again, and we arrived just in time to watch. That reframing changes what Phoenix A means. It is not only the largest black hole we have found, and an object whose formation we cannot fully explain. It may also be a window, a rare chance to watch a piece of cosmic history that we thought we could only ever infer from its aftermath. The assembly of giant black holes was supposed to be something we reconstruct, like detectives working backward from old evidence. Phoenix offers the possibility of watching it more directly, a fragment of the ancient past still in motion, still pouring gas onto a growing giant, still lighting up a galaxy with the fury of creation, all of it captured in light that has been travelling toward us since before the Earth existed. It is worth asking how long this broken balance can last, because it tells you something about how rare it is that we caught it at all. The runaway in Phoenix is not necessarily permanent. A feeding event like this, however dramatic, is a phase, and phases end. It is possible that the black hole will eventually pull ahead, that as it grows and its jets strengthen, they will finally overpower the inflow, reheat the gas, and restore the balance, sending Phoenix back toward the quiet equilibrium of an ordinary cluster. It is also possible that the cooling flow will run for a long time yet, hundreds of millions of years more, building the central galaxy into something even more extreme before it finally exhausts itself. Either way, on the immense clock of the cosmos, the awake phase is likely brief, a passing chapter in the life of a cluster that has already existed for billions of years and will exist for billions more. And that is precisely what makes our timing so remarkable. To find a cluster in the middle of this rare, temporary breakdown of its thermostat is to have arrived, by luck, during a short act in a very long play. There is a humbling symmetry in what that means. We think of the early universe, the era when the first giant black holes were assembling in unchecked floods of gas, as a closed chapter, something we can only ever study second-hand by piecing together clues from its aftermath. But the universe, it seems, is willing to occasionally rerun the old process, in isolated places, under the right rare conditions, long after the era of assembly was supposed to have ended. Phoenix is one of those places. It is a pocket of the young cosmos reassembled in a later age, a fragment of the universe's violent childhood still playing out where the balance happened to fail. And because it is nearby enough, in cosmic terms, and loud enough to notice, we get to watch a process we thought we had missed by billions of years. It is a second chance to see the machinery of creation running, granted by nothing more than the accident of a single cluster's unusual shape and quiet past. And that thought, that we are seeing something ancient still happening, is the doorway to the strangest part of the whole story. Because if Phoenix caught the early universe in the act, then the light we are collecting is not just a picture of a black hole, it is a message across great spans of time, and to receive it, we have to reckon with just how far and how long it travelled. Let me take you all the way out to the far view, so you can see the whole system at once, the firestorm and the jets, and the invisible territory at its centre, and feel the distance that separates that light's departure from its arrival. Part 11. A live view of the ancient universe. Imagine you could stand outside the central galaxy of the Phoenix cluster, far enough away to take in the whole picture, but close enough to feel it. This is a place no one will ever go, and I am asking you to go there anyway, because seeing the whole system at once is the only way to feel what it is. The galaxy itself glows, not with the steady, familiar light of a settled galaxy like our own, but with the heat of hundreds of millions of newborn stars packed into a region not much larger than the Milky Way. It is a furnace of creation, a place where suns are igniting faster than anywhere you have ever imagined, so many at once that the whole galaxy burns with the accumulated light of its baby boom. The space around it does not look empty. It shimmers, filled with the faint, fierce glow of plasma cooling from tens of millions of degrees, the great gas reservoir pouring inward, lit up in X-rays across a scale of millions of light-years, and from the very centre of the galaxy, from the lowest point of the whole structure, you would see jets, beams of high-energy particles punching outward at nearly the speed of light, straight out from the poles of the black hole, slamming into the surrounding gas and carving out cavities the size of small galaxies, hollowing spaces in the reservoir large enough to hold everything you have ever known. And above all of it, invisible but unmistakable in its effects, is Phoenix A itself. You cannot see it directly. It gives off no light of its own, but you can see everything bending toward it, the jets erupting from it, the gas spiralling down into it, the whole galaxy organized around the pull of it. It is a pit in space-time large enough to swallow our solar system 100 times over. It is not gleaming, and it is not glowing, and it is not even truly dark. because the matter falling into it, the gas racing down toward that 3-week-wide boundary, heats to a white-hot fury and blazes with its last light in the instant before it disappears. Around the edge of the invisible territory there is a ring of brilliance, the final glow of everything about to cross a border it will never cross back over. And at the centre of that ring, there is simply a region where the universe, in any meaningful sense, ends. Hold that whole picture in your mind. The firestorm of newborn stars, the shimmering infall of cooling plasma, the jets carving out galaxy-sized hollows, and at the centre of it all the silent, invisible, immense pit around which the entire system turns. That is the Phoenix Cluster's centre. That is what the faint smudge on the light of the Big Bang turned out to be when we finally looked. Now here is the part that turns the picture from wonder into something closer to reverence. Everything I just described, the whole living system, is not happening now. It happened 5.7 billion years ago. That is how long the light has been travelling to reach us. When that light left the Phoenix Cluster, the Earth did not exist. There was no sun in our corner of the galaxy, no planets, no oceans, no life. The atoms that would one day become the ground under your feet were still scattered in clouds of gas, waiting to be gathered into a star that had not yet formed. Think about what happened in the time that light was in transit. It left the Phoenix Cluster and began crossing the emptiness, and while it travelled, our entire world came into being. A cloud of gas collapsed into our sun. Dust and rock gathered into planets. The Earth formed and glowed molten and slowly cooled. An atmosphere gathered around it. Oceans condensed. Life appeared, first as the simplest possible things, and then, across billions of years, grew and diversified and complicated itself until it produced creatures that could look up and wonder and eventually build telescopes and carry one to the bottom of the world and point it at the sky. And at the very end of all of that, after the light had crossed 5.7 billion years of space, it finally arrived and fell into an instrument on the Antarctic ice and told us that Phoenix A was there. The light is a message that was sent before its receiver existed, and it arrived exactly when a species had finally grown ready to read it. This is one of the strange and beautiful facts about looking out into space, and Phoenix A carries it to an extreme. Every time you look at something far away, you are looking into the past because the light took time to reach you. But usually the past you're seeing is modest. A few minutes for the sun, a few years for the nearest stars. To look at Phoenix A is to look across a span of time longer than the age of the Earth. You're not seeing the black hole as it is. You're seeing it as it was when our world had not yet begun. What it is doing now, in the true present, 5.7 billion years further along, we cannot know and will never know because that light has not been made yet and will not reach anyone here for ages after all of us are gone. And that opens onto the thought I find hardest to set down, the one underneath the size and the math and the mystery of its origin. Each step outward in the history of astronomy has made us smaller. For most of human history, the largest things we could imagine were the things we could see: mountains, oceans, the horizon. Then we learned that the Earth itself was a sphere, drifting in space, and that the Sun was far larger, and that the Sun was one of hundreds of billions of stars in a galaxy, and that the galaxy was one of hundreds of billions of galaxies. Each discovery made the ground beneath us feel a little more like a footnote. Each step outward taught us that what we had thought was big was, in truth, a small thing seen up close. I want to give the immense span of time in that light its full measure, because it is easy to say 5.7 billion years and let the number wash over you without feeling it. Consider that the entire history of complex life on Earth, from the first simple many-celled creatures through every animal that has ever crawled or swum or flown, fits several times over inside the span that light was travelling. Consider that if you could somehow have watched the light on its journey, it would have been in flight for longer than the Earth has had continents in their current arrangement, longer than there have been mountains where the mountains now stand, longer than almost anything you could point to as ancient. The pyramids, the oldest human structures, are a few thousand years old. The oldest rocks on Earth are a few billion. The light from Phoenix A has been crossing space longer than the Earth has existed at all. When it left, our planet was not late in forming. It had not begun. There was only a cloud of gas that would, across the whole long transit of that light, slowly become everything. And there is a quiet vertigo in realizing that the reverse is also true. If, somehow, there were an observer in the Phoenix cluster right now, in its true present, and they turned an instrument toward our corner of space, they would not see us either. They would see the light that left here 5.7 billion years ago, a young galaxy with no Earth in it, no sun where the sun now shines. We cannot see each other as we are. We can only ever see each other as we were, separated not just by an unbridgeable stretch of space, but by an unbridgeable stretch of time, each of us forever looking at the other's distant past. The light is a thread, but it is a one-way thread into history, and no message and no glance can ever reach across it to the present on the other side. Phoenix A, as it truly is right now, is not a thing anyone here will ever witness. We have only its ancient face, and even that is a gift, arriving exactly when we finally grew able to receive it. Phoenix A is the next footnote in that long humbling. A black hole so massive that our standard idea of a black hole cannot quite hold it. A region of space so large that light needs weeks to cross it. A presence so heavy that it binds together a cluster of galaxies more massive than anything in our local part of the universe. And it is not even unique. It is one object among what may be very many, in a universe filled with structures we have only begun to find. To really take it in is to feel yourself shrink one more time, to feel the scale of your own life and world settle into proportion against something that was already immense before the Earth was born. And the light, the ancient light still arriving, is the only thread connecting that faraway giant to the small warm place where you are sitting, listening, right now. Part 12. The Ones We Can't See. There is one last turn in this story, and it is the one that lingers longest after the numbers have faded, so I have saved it for the end. If Phoenix A exists, then it is almost certainly not unique, and once you follow that thought to where it leads, the dark gets a great deal larger. Remember how we found it. We did not discover Phoenix A because we set out to find the largest black hole in the universe. We found it by accident, because its host cluster happened to be doing something loud, that broken thermostat, that runaway cooling flow, which lit the whole system up in X-rays and left a mark on the oldest light in the sky. The black hole itself gave off no such signal. It was the cluster's dramatic behaviour that caught our attention, and the black hole was simply sitting at the centre of the drama, which means our detection depended entirely on Phoenix being an exception, on it being awake, on the thermostat having broken. If the cluster had been behaving itself, if the balance had held, there would have been no firestorm, no runaway flow, no bright X-ray beacon, and the black hole at its centre, 100 billion solar masses of it, would have gone on sitting there in silence, and we would never have known. So ask the obvious question, how many others are there, sitting quietly that we cannot see? The black hole itself, the one at the centre, may be only one of many ultramassive black holes scattered throughout the universe. Most of them quiet, most of them dark, most of them, crucially, invisible to our current telescopes precisely because they are no longer feeding. A black hole that has finished its meal and gone dormant gives off almost nothing. It does not blaze, it does not drive jets, it does not light up its surroundings. It simply is, an immense silent territory, giving no sign of itself, undetectable by the very method that revealed Phoenix. We found the one with the lights on. We have almost no way of counting the ones sitting in the dark, and it may go further still. There may be black holes out there with masses well above 100 billion times the Sun. Some theorists have started using a phrase for these hypothetical giants, calling them stupendously large black holes, objects so enormous that they begin to push against the upper limits of what our theory of gravity, general relativity, appears to allow. We do not know how many there are. We do not know exactly how they formed. We do not know what role they play in the long-term fate of the galaxies and clusters they anchor. We only know that Phoenix A exists, sitting near the edge of what we thought was possible, and that if the edge has one object on it, the region beyond the edge is unlikely to be empty. There may be a whole hidden population of the largest structures gravity can make, waiting in the dark, and we have caught sight of exactly one of them, and only because it was misbehaving. There is a strange comfort available here if you look for it, though it sits right alongside the unease rather than replacing it. The hidden giants are not a threat. They are not coming for anything. Most of them, if they exist, have been sitting quietly for ages, doing nothing, changing nothing, harming nothing, simply holding their positions in the far dark between the galaxies. The image of them as monsters lying in wait is a projection of our own instincts onto objects that are, in truth, utterly indifferent to us and to everything else. They do not hunt. They do not stir with intent. They are regions of space, bounded by gravity, patient beyond any meaning the word usually carries. The unsettling thing about them is not that they are dangerous. It is that they are there at all, so many and so large and so completely beyond our reach or our full understanding, and that we have only just begun to suspect how many there might be. And perhaps that is the honest emotional truth of the whole subject, the thing underneath both the wonder and the unease. To learn about Phoenix A is to be reminded, gently and completely, of the scale of your own smallness against the universe, and to find that the reminder is not cruel. It simply is. The giant does not care that you are small. It does not care that it is large. It has no opinion about the civilization that built the telescope that found it, or about the fact that its light arrived exactly when a curious species was finally ready to read it. It only continues. And there is a kind of peace available in that, if you're willing to take it, the peace of setting your own worries down for a while beside something so immense and so old and so entirely unbothered that it puts every urgent thing in its proper proportion. This is where the phrase from the beginning comes back around, and I want to give it its full weight now. Not an object, a territory. When we first said that, it was about a single black hole, a way of capturing the fact that something light takes 3 weeks to cross is not a thing but a place. But the word means more than that now. The universe may be dotted with these territories, most of them silent, most of them invisible, immense regions where the ordinary rules give way, scattered through the dark between the galaxies. What we found at the centre of Phoenix is not just one strange object. It may be our first clear look at a hidden geography, a class of the largest places gravity can carve, and the map of them is almost entirely blank. And the thermostat, that broken balance, means more now too. When we said the thermostat was broken, we meant it literally, the failed feedback loop in one unusual cluster. But there is a second, quieter sense in which it applies to us. Our confident picture of the universe's largest objects, the tidy story with its 2 families and its comfortable ceiling, was its own kind of thermostat, a mechanism for keeping our sense of scale in balance, for reassuring us that we knew roughly where the top of the world was. Phoenix A broke that too. It poured in from above the ceiling and showed us that the balance we felt was never real, only unexamined. The regulator that kept our understanding calm has fallen behind the universe it was trying to describe, and there is no putting it back. Once you have seen an object our rules say should not exist, you cannot return to believing the rules were complete. Think about what a hidden population of these giants would actually mean for our picture of the universe, because it is not only a matter of counting objects we have missed. The largest black holes anchor the largest structures. They shape the galaxies and clusters around them, regulating star formation through exactly the thermostat we have been discussing, heating and stirring the gas, deciding across cosmic time whether new stars are born or the gas stays too hot to collapse. If there is a whole quiet class of ultramassive and even larger black holes scattered through the universe, then they have been shaping their surroundings all along silently, in ways we have not accounted for because we could not see the objects doing the shaping. Our models of how galaxies grow, how clusters settle, how gas turns into stars across the history of the cosmos, all of it assumes we know roughly what the central engines are. A hidden population of the largest engines would mean our accounting is incomplete at the very top, where the heaviest objects exert the most influence, and there is a genuine limit set by physics itself on how far this can go, which is part of why the largest examples are so tantalizing. General relativity, our theory of gravity, does not forbid black holes of any particular size outright, but the ways they can form and grow do run into constraints, and the very largest hypothetical objects, those stupendously large black holes above 100 billion solar masses, sit near the edge of what those constraints seem to allow. Studying them, if we can ever find the quiet ones, would be a way of testing our understanding of gravity at the most extreme scales in existence, pressing our theory against the largest objects it will permit and seeing whether it holds. Phoenix A, sitting where it does, near that upper edge and lit up for us by the accident of its broken thermostat, is the closest thing we have to a specimen from that frontier. It is a single data point at the top of the scale, and the fact that it exists at all tells us the frontier is real and populated, and mostly still hidden from us in the dark. So let me leave you where the object itself leaves us. Somewhere out there, 5.7 billion light-years from where you're sitting right now, a hole in the universe is open. It opened long before the Earth formed. It will still be open long after the Earth is gone. And in the time it took for its light to reach us, every atom of your body, every breath you have ever taken, every moment you have ever lived came and went, while Phoenix A simply continued doing what it has always done. That is the part that stays with me. Not the size, not the math, not even the mystery of how it came to be. It is the continuity, the fact that something so enormous can be so patient, that it can wait through the rise and fall of entire civilizations, outlast suns and planets and whole species, and still, at the end of all of that, be hungry. It does not rush. It does not announce itself. It does not need to. It only has to be, and to wait, and to go on being what it is long after everything that ever noticed it has gone quiet. We have spent this whole time learning what Phoenix A is, the largest black hole we have found, and maybe not the largest that exists, an object our own rules say should not fit in the time the universe has had, a giant that slept for ages and then woke, and is feeding still, in a cluster where the great balance has failed, a territory rather than a thing, a place rather than an object, a border you could cross without ever feeling it close behind you, still awake, still feeding, still hungry, in the only light of it we will ever have. And perhaps that is the quiet lesson underneath all of it, the one worth carrying with you as you drift off tonight. Sometimes the most unsettling thing about the universe is not what is loud. It is not the explosion, the collision, the sudden violent event that grabs the eye. Sometimes the most unsettling thing is what has simply been waiting. Out there in the dark, patient beyond any scale we can feel, are the largest things gravity has ever built, most of them silent, most of them unseen, doing nothing at all for now. Phoenix A is the one that happened to stir while we were watching. The others are still out there, still quiet, still keeping their own time, and the universe, as it turns out, is far more patient and far more full of waiting giants than any textbook ever let us believe.